Alright, so today we're going to prove the fundamental theorem of calculus. This is a pretty cool and fundamental proof that everyone should know. And it's not that hard to actually understand, even for high schoolers. So this is really, I would definitely have this in your mind and then tell your high school teacher of AP Calculus BC or AB, just kind of flex that you can do this proof. So what do the FTC and FTC inverse as well? We need to know what both of them say before we dive into the proof. Okay, so here's theorem 1, which is also FTC. If f prime, cap f prime, is continuous on closed AB, then the integral from A to B of cap f prime of x dx is just cap f of b minus cap f of a. Or this is just really saying that f is an antiderivative. Now I'm going to turn off my notifications because that's just really annoying. From here, all we have to do is just then we need to state what FTC inverse is. So here is theorem 2, which is FTC inverse. And this just says that if f, lowercase, is continuous on the closed interval AB, and f is cap f is an accumulation function, that is defined to be and all that we're saying here is that for all x and x in AB, or better notated as this, then f, cap f, is differentiable on AB, and its derivative is just f. Okay? Or f of x, which is really just saying that cap f prime of x is just f of x. That's what it's really saying for all x in AB. This just means for all x in the interval. Okay, so just to restate all of this, all we're saying is that the fundamental theorem is saying that f is an antiderivative of f prime, and if cap f is an accumulation function from a to x of f of t dt, then the derivative of that accumulation function is just f as well. Now, in order to prove that FTC works, we need to prove this first. So that's our starting point. Now, just to make sure this is really clear, a lot of people will write the conclusion of this theorem as just basically saying that the derivative of a to x of f of t dt is just f of x. So that's just the basis of everything. Okay, so we need to show that f cap f prime of x equals f of x by the definition of derivative. Okay, I don't think I spelled. Okay? So, cap f prime of x is equal to the limit as h approaches 0 of cap f of x plus h minus cap f of x all over h. And here we can we can bring this h outside of the limit just to make things look very nice. This is really just 1 over h times the limit as h approaches 0 of, and by the way, this is just what the definition of derivative is. What we do is now we're going to plug in, the accumulation function. Because remember, we set up here that this is this. So we need to bring that down there. Okay? So let's keep going. So remember, cap f of x plus h is really just the integral from a to x plus h of f of t dt. Why is that so not right space right? F of t dt. And then of course you just minus f of cap f of x, which is just integral from a to x of f of t dt. Okay. Now, just simplifying this is really just 1 over h, limit as h approaches 0, and the x's of the upper limits will cancel out when we subtract the two integrals, because the integrand is the same, so it'll just be the or not the x's, the a's will cancel out. So this is really just 1 over h times the limit as h goes to 0 of from the integral from x to x plus h of f of t dt. Hopefully you guys see what happened there, because this is just a bigger distance away. So if you had this thing would be like h, so this is x plus h, and if this is a, it's just this part of the integral that we're looking for. Okay, awesome. So we're at this now, and this looks pretty neat. And we need to show that this is basically f of x. That's what we need to show. And there are two cases that we're going to need to consider when h is less than 0 and when h is greater than 0. Most proofs, including this one, will just focus when h is greater than 0. The other one is just going to have a ton of negatives. Okay. So we're going to concentrate, we're going to focus on the values of f on the interval from x to x plus h. And by the extreme value theorem, if you guys remember, on a closed and continuous interval, there are extreme values, right? A maximum must take on a maximum or a minimum. For example, let's just take a random function. On this interval a to b, it must take on a maximum or a minimum, right? This is the minimum, this is the maximum on AB. Even if it was, let's say, something like this. This is the maximum, this is the minimum. So just extreme value theorem, really simple. It's just saying that there's a maximum and a minimum on a continuous function on a closed interval. In this case, this is going to be our interval. And we're going to find what these, we're going to basically define the max and mins and use the squeeze theorem. And you'll see how that happens. So, in this interval, f takes a minimum, which we're going to define as mh, and a max, which we're going to define as m cap m h. Okay, so this is by the EVT. So since the minimum of h is less than or equal to f of t is less than or equal to the maximum of h, on a maximum value on the continuous closed interval, on the interval from x to x plus h. Therefore, and that's what therefore, this is the symbol for therefore. Therefore, we can, when we take the definite integrals, we're going to have, on this interval, we're going to have the integral from x to x plus h of the minimum value of h, dt, must be less than the integral from x to x plus h of f of t, dt, which is also less than or equal to the maximum integral. Now, here's the thing, guys. We know that the integral from x to x plus h of the minimum h dt is equal to h times the maximum, h times the minimum of h. And similarly, for the maximum value, this is literally just equal to h times the maximum of h. So, with this in mind, let's divide everything here, now knowing that we can substitute this into this and this into this. We're going to divide by h, by everything. So the resulting inequality will just leave us m, the minimum value, 1 over h times the integral of x to x plus h of f of t dt, which is also less than the maximum of h. And so in here, remember guys, what does this look like? This looks a lot like this, but without the limit. So all we're going to do here, guys, is we're going to take the limit of everything as h goes to 0 of all of this. So, on the interval x comma x plus h. But wait, guys, look at this. All of them on this interval are approaching f of x. Do we see that? Both the minimum and the maximum values approach f of x. Okay, do we see that? As h goes to 0. Because this distance is shrinking. Okay, so maximum, right? These are going to f of x, the function itself. From here, because they're both going to f of x, by the squeeze theorem, which basically says that if h is less than or equal to f is less than or equal to g, and the limit, and the limits are the same, then f is squeezed in between them. In this case, because both of these guys decide to go to f of x, that means this must also go to f of x because it's squeezed in between them. It's between them. So 1 over h, and 0 from x to x plus h of f of t dt, as h goes to 0, must go to f of x. And there we have it. So we just showed, we have just proven that cap f is equal to f. Okay, so this is the proof of FTC inverse. But we are here to prove FTC, so let's get back onto track. Okay, so now we're going to prove FTC. And you're going to see why we needed to prove FTC inverse. So we're going to let g of x equal to the integral from a to x of f prime of t dt. So by the FTC inverse, why do I keep writing I? We know that g prime of x is just f prime of x, or cap f prime of x more specifically. And we know that therefore these only differ by a constant. Constant c. Okay? So what that's really just saying is that g of x minus f of x is just some arbitrary constant for all x. Actually, I don't even know if that's the symbol, but I think it's just for all x on the interval from a to b. Okay? We know that g of a is equal to the integral from a to a of f prime of t dt, cap f, of course. And that's 0 because the upper limits are the same, right? These are the same upper limits. The integral from 1 to 1 of anything is just 0. There's no area, there's no distance you covered for that function. Okay, so we know that. And g of a minus f of a is also equal to the constant. So c is just negative f of a because g of a is just 0. We just showed that here. Okay, bear with me. We're almost there. So, that means that g of x minus f of x is then equal to negative f of a. Do you see that where that came from? That came from the original statement we made over here. We said that they differ by a constant, and we figured out that that constant was just negative f of a from the accumulation function that we defined earlier. Okay, so we're almost done. This is true for all x on the interval a to b. And g of b, which is another constant, an upper limit, you could say, a is the lower limit. We also know that g of b minus f of b is also negative f of a. So g of b is just f of b minus f of a. But wait, what do we define g earlier? Remember, recall that g of x was equal to the integral from a to x of f prime of t dt. And so g of b is really just the integral from a to b of this. But this is also equal to this, which is f of b minus f of a. And therefore, the proof is complete. So, FTC proof. There it is. Well, we just showed, hopefully you guys saw it, because remember, we defined g as this function. We found g of a, and we know that they differ by a constant. And when we plug in b, an upper limit of because it's g of x, and if we plug in b for x, we see that the integral from a to b of f prime of t to t is f of b minus f of a. In other words, the antiderivative. There it is, guys. Super cool proof, super fundamental, super fun. Have a good day, guys.